And it is December now, I think. Yes, December 2nd. And this is the last chapter of the semester, chapter 15, Radical Chemistry. Quiz 9 from chapter 14 is due tonight. So be wrapping that up. I helped quite a few people in office hours. I've talked to the TAs, and yeah, I think that last problem's a little tricky. Give you a little hint there. You need to come up with a halogen. There is an M plus 2 ion in the mass spec with a 3-to-1 ratio. That should give you an idea of what halogen it is. And one more hint, let me help you out here. That halogen creates a stereocenter in your target structure. And that means there's the possibility of diastereotopic methylene hydrogens, which will make part of the spectra look kind of complex. And some of you, I think, figured that out okay, but I thought I'd share that hint with you. Let's see, homework 15, the last homework will be due next Monday. We got a couple class periods on 15, and then yeah, we're wrapping up pretty quick here. After we finish 15, yeah, we'll have test 4, which will be next Tuesday, all online, multiple choice. Stay tuned for that. And then the final, we'll talk more about that. But the sample test 4 is, of course, already on Learning Suite, and so is the sample final. Be looking ahead, be reviewing all the chapters. The final is, of course, comprehensive, all 15 chapters. So be reviewing that material to prepare for that. I think that's everything we need to talk about now. Yeah, okay. All right, before we jump into 15, I've got a couple things to catch your attention here, maybe. A reaction run by Moses Gomberg at the University of Michigan about 100 years ago. He took this triphenyl methyl bromide and he treated it with finely divided silver metal. And he got a strange product. He got a product that was C19H15, the mass spec 243. He didn't know what that structure was. He got a byproduct of silver bromide. Okay. But yeah, 243, does it have nitrogen in it then? No. There's no nitrogen here to begin with. And the bromide ends up on the silver. So what is this product? Well, he finally figured it out, and it looks like this. Remember, phenyl corresponds to benzene rings. And what's right here, if you pull off this bromine atom here, you just get this radical right here. Trivalent carbon? Wait a minute, we've been telling you the whole time that carbon is tetravalent, 4 bonds, right? No, there is this form of carbon called a radical, free radical, which only has 7 total electrons around it. And this is an unusual radical. This has, with the 3 the benzenes here, it can, by resonance, delocalize this. We call this a persistent radical. It's still unstable. It'll eventually dimerize. But Moses was very confused about this. Trivalent carbon, it was the first time. We know a lot of different ways to make now radicals. Carbon with odd electrons, 7 electrons, and that's what we'll be talking about in chapter 15 here. But yeah, you can see how that works there and add up the weights there for that persistent triphenyl methyl radical of Moses Gomberg. Another thing here to catch your attention a little bit. How about dental onlays? We've all had cavities filled, I think. Maybe some of you have been very good brushing your teeth and haven't had any cavities. The rest of us have had to sit in the dental chair with the drill and everything, and finally they do the onlay with the polymer and the composite materials. Maybe you've asked the dentist about that, and a lot of you want to become dentists, so I think this is a good topic. What's this blue LED light, that gun they put in there? Once they get the onlay and everything ready to go, they always shine that blue LED light in there for a few seconds. What's that all about? Well, it's this camphor ketone, which is the initiator for a radical reaction with this cyanoacrylate material here. This is a cyanide, an alkene, and an ester here. This is the monomer, which will become a polymer, okay? And so radical chemistry can make a lot of these polymers. You've probably heard of polystyrene, polyvinyl chloride, whatever. But the LED light excites the ketone to the excited state, We'll see it later. We'll draw the diradical, the initiator here, which adds to the alkene, and then it propagates. It puts together a bunch of those cyanoacrylates to make a polymer. So this chain can be hundreds or even thousands of units long. It becomes a solid material that intercalates into the little micro holes in the surface of the tooth, and if you're getting a crown or whatever, and that effectively locks it in place on your tooth, making this polymer. But the blue LED light is part of the initiation. We'll see light activation as a means of making polymers. So there's a couple things for you to catch your attention. Let's go to the overhead here and go through the topics and see what we need to know. I'm glad to report today that there's only 4 new reactions we need to learn. So for test 4 here, we've got the reactions, in chapter 12. I think there were 8 of them. Remember those oxidation reduction reactions? And here there's 4 more. So there's 12 reactions you need to keep track of for test 4. And we'll be clear about that. We'll talk about radicals and what they are, 7 electrons, the dot here, they're neutral, whatever, and how stable they are, the different types there. And then we'll talk about alkane halogenation here. So we'll take alkanes, treat them with bromine or chlorine with heat or light, and make the alkyl halide. Now we've formed halides before from alkenes, but now we're forming halides from alkanes. Alkanes are much more abundant from petroleum and other sources. They're cheaper than alkenes. So this means of making alkyl halides from alkanes becomes a very important industrial process. So I'll show you some of those, how they work. We will be limited to bromine and chlorine. Fluorine is just too reactive, too explosive, and iodide's just too slow normally. But with light, activates, so here's H nu with light, you can do this at room temperature and just get monohalogenation to occur. If you use heat and excess chlorine or bromine, you often get overhalogenation. And they're selective here. Chlorine is somewhat selective for tertiary and secondary positions here. This is the relative rates of substitution at tertiary, secondary, primary positions. But look at bromine here. Highly selective, 1,000 times faster than primary and much times faster than secondary positions. So the relative rates here for bromination at more substitute positions is much more pronounced. Bromine turns out to be more useful synthetically in a lot of ways. Chlorine's cheaper, and if you can separate them out, that's okay. We'll look at the selectivity. So there's quite a bit to talk about here for this industrially important reaction of halogenation of alkanes, anyway. And we'll relate it to synthesis. Once we have a halogenated alkane, alkyl halide, whatever, we can do all the substitution or elimination reactions and then really open up a lot of synthetic possibilities. So that's the thing. We got 12 reactions for test 4, that because of the versatility of forming an alkyl halide, we open up a lot more synthetic possibilities. But we'll keep them just, 2 or 3 steps. If you use the reactions and analyze things forward and backward direction, you should. Because stereochemistry, the radical is a flat trigonal planar structure, so it loses a stereocenter at that point if there is one. Generally, we get achiral or racemic products, okay, because of the planar radical thing. All right, a couple other things to talk about in radical chemistry. Ozone, we won't talk about that, O3. We used ozone to cleave alkenes, remember, in chapter 12. Ozone is a radical degradation compound that will be dissipated in the presence of chlorofluorocarbons, which were used as refrigerants a lot of times. These released into the atmosphere then degrade the ozone layer in the upper atmosphere. If you want to read about that, you can in that decomposition process. I won't ask about that on the quiz or test, so you can just read that and appreciate that anyway. The other reactions, I think there's 3 more. Allylic halogenation, if we have an alkene here with NBS and light, or bromine at low concentration, we can get allylic bromination to occur. We've used NBS before for the bromohydrin reaction. Peroxide initiator, or light to initiate it. There's a couple variations of how we run these reactions. We can also talk about the properties of radicals and how they're trapped with oxygen. So that's maybe a tie-in to some biological topics that maybe you've heard about. Free radicals in the body causing damage, damaging lipids or genetic material, DNA. Um, and oxygen can actually initiate that. And there are certain traps in the body that shut that pathway down, which is vitamin E and vitamin C, actually. BHT is a food preservative to keep polyunsaturated fats in food from going rancid. We'll kind of relate that, tie those two topics together just a little bit. So there's an interesting. The last two reactions involves anti-Markovnikov addition of HBr to alkenes in the presence of peroxide. So it initiates the radical process. Remember, we've used HBr before with alkenes to give the Markovnikov product, right? Giving the more substituted bromide. Now, in the presence of peroxide, we get the less substituted bromide, okay? The so-called anti-Mark product. We'll see how it works. It's really limited to bromine. Chlorine doesn't do it as well. Well, wait a minute, that's just the carbon radical, yeah. We'll just stay limited to bromine for this, yeah, so HBr. And then polymers, we just showed you the dental application. There's many, many more here. Polyethylene, polyvinyl chloride, polypropylene, Teflon, which is polytetrafluoroethylene. There's many others, polystyrene. We'll show you how in the presence of a radical initiator and alkene, there's no other reagents, we'll just zip together and make these long chain hydrocarbons. And whatever else is on the alkene kind of goes along for the ride. This is the simplest one. This is ethylene polymerized to make polyethylene, which you've probably heard about. But we'll show you that, get into that a little bit. All right, let's go to the board here and see what we need to know. Go through the structure of radicals and some of the characteristics of them just in general. And what we need to know here. So radicals are these odd electron species. Count up the total electrons around the radical. What's that? 7 electrons, okay? So this violates the octet rule. We call this an open shell species. So it's relatively unstable. We've talked about these before, right? Carbocations, where we have 6 electrons at a plus charge. Notice radicals are neutral, right? Count it up here. What's the formal charge on this carbon? How do you do the formal charge thing again? Valence electrons minus bonds, 1, 2, 3 bonds, minus unpaired electrons. How many? Just 1. So yeah, the formal charge is 0. They're neutral. But they're very reactive because it's 7 electrons, okay? So these will be new intermediates that we'll look at. Moses-Gomberg's triphenyl methyl radical is kind of unique in that those 3 phenols highly stabilize that. And that's another thing we need to get into. But they're not carbocations. They're not carbanions. If we have 2 electrons there, it's negatively charged. So you can look at radicals as just a different intermediate, okay? Most reactions involve these kind of intermediates. The more rare reactions are these radical reactions, but they're important. There's a lot of important reactions here. And we'll see how the conditions are changed to make it go via a radical pathway, okay? Usually these come from bond homolysis type processes. So we've talked about this. And what do we mean homolysis? Both intermediates wind up with the same species here. So if this bond breaks apart with 1 electron going to B, the one going to A, you're just generalizing this. This is what homolysis, homolysis. Lysis means to break. Homo means both things end up in the same state there. They're both neutral radicals. Okay, what about stability here? We've got radicals. What types can we have? Well, we can have methyl radical, okay, highly unstable, just with the 3 hydrogens on there. That's not as stable as a primary radical, okay? So if we draw it like this, I'm not designating the carbon, but if this is just on the end of a chain there, that would be a primary radical, okay? More stable is a secondary radical. And you see there, you've got 2 carbons on there. And don't forget about it has a hydrogen there too, okay? Secondary radicals are more stable than primary, and tertiary more stable than secondary. So what does this follow? This follows the same relative stability pattern we saw before with carbocations. So what do you think is the main factor driving this? Right, it's more carbons that you have around here, so it's an inductive effect of helping to stabilize that intermediate, okay? But what is the radical? What molecular orbital is that in? Right, it's in a p atomic orbital. So we'll have to look at the structure of that and see what the geometry of that's going to be. It's trigonal planar, actually, okay? Because it has 3 bonds to it. What about the p atomic orbital, though? It's half filled, we say. Okay, it's not empty like a carbocation, but it does have a dearth or a lack of electron density, just having the 1 electron in it. These are also similar in stability to allylic radicals. And what's the stability there? Or benzylic radicals, okay? So if we can have a carbon next door to a benzene. So that's similar to the Gomberg triphenyl methyl radical. And why are these so stable? These are similar to the tertiary radical stability. And you might say, well, that looks like a primary position on the end. No, what other effect do we have here? Resonance, right? So in addition to the inductive effect, we also have the resonance stabilization. So can we draw a resonance contributor here? Yeah, so if we draw this, what do we get? We move the radical over to that position, okay? And that delocalization helps stabilize this, okay? And we see this in the bond dissociation energies also. If you take off of a primary position, that's harder to do than taking it off of a tertiary position. So we'll see some of the reactions here. We'll have like a radical that will take off a hydrogen atom and leave behind the carbon radical. And we'll get into those types of reactions with radicals, but here's the relative stability. Let's look at the structure a little more carefully. So here's our carbon, and if we've got, some other groups on it, and then 1 electron there. Yes, it is trigonal planar, it's flat. So what's the hybridization of this carbon? We could say, yeah, it's sp2 hybridized. Okay, so this is a p atomic orbital that's just half filled there. And so we don't talk about the HOMO and the LUMO like we did in heterolytic chemistry with cations and anions, nucleophiles, electrophiles. Here we actually have a new term called SOMO. And almost sounds like a sumo wrestler in Japan. No, it's not. It's different than that. SOMO, what does that stand for? HOMO is highest occupied molecular orbital. LUMO is lowest unoccupied molecular orbital. So SOMO is singularly occupied molecular orbital. So the single occupation is the one electron there for a SOMO. There are some consequences to this. They are electron deficient, similar to carbocations, you could say. And that's because, it's half filled, or is it half empty? Well, it's more half empty, you'd say. So it's deficient in its electron density. So similar to a carbocation in that way. But it is different here. Radicals do no rearrangements. And remember, rearrangements were very typical, especially with branching on what? Carbocations, to go to a more stable carbon with one shift. Why no rearrangements with radicals? Well, let's look at this. So if we've got a primary SOMO here, and we've got some branching next door, why can't we do that shift? Because before we had the carbocation here, right? And if we had anything branching wise, we could do that shift very easily to go to the rearranged products, right? Why can't we do that now with radicals? Well, here with the empty orbital, this is just 2 electrons moving over, right, to go to the more stable carbocation. So that's okay with an empty orbital here, right, where we have a LUMO, lowest unoccupied molecular orbital. But here it's singly occupied. And if we were to move these electrons over, notice the double-headed arrow, If we were to do that, that would involve 3 electrons going into a single molecular orbital. And that's a violation of quantum mechanics. You cannot add more than 2 electrons spin paired to any given orbital. Okay? So this cannot occur. And normally we don't see any rearrangements. It's really a hallmark of radical chemistry versus cationic chemistry via cations. But anyway, no rearrangements, kind of a minor point. Don't worry about that. It simplifies things, I think, in a lot of ways. Let's look at reactions in general for radicals. And the reaction types here, there's generally 2 types of reactions we're going to look at. And that involves where you have some sort of radical, already kind of showed it. If you have some radical intermediate or reagent here with a singly occupied orbital, you can take this atom off and leave behind the electrons there. So, you know, we're kind of combining those electrons. And what we end up with is the radical on carbon here and what? HX, okay? So you see this radical combined with 1 electron here, and then 1 electron on this bottom. Remember, each line's 2 electrons, okay? So 1 stays on carbon. This is called abstraction. And we'll see that in alkane halogenation, of course. That's a typical type of reaction for radicals. Another one is additions to alkenes. So this is a little bit different. Here we've got our radical again. But instead of extracting an atom, you say on an alkene, it's already sp2 hybridized. It's harder to take off these sp2 hybridized carbon hydrogen. It's much easier to abstract these from sp3. So that's another thing. Abstraction from sp2 positions is a lot slower. Why? That bond dissociation energy is stronger. And plus, if you leave the radical on the side of an alkene, it's perpendicular to the pi bond. It's not resonance stabilized. We'll see abstraction at the allylic position, but right now I'm just pointing this out. Instead here, you can have an addition to an alkene, which will look like this. You'll form a new carbon X bond and form a carbon radical there, okay? So that's not an abstraction, this is an addition, okay? There's one other type, and that's termination, where you have 2 radicals coming together. In termination, we haven't talked about the mechanism yet of halogenation. It's a way where 2 radicals can couple together, okay? And if that occurs, you see it goes back to the neutral thing, and both radicals become closed shell. Both get the octet. This is far less common. Remember, I said radicals are high energy species, intermediates. So to have 2 high energy species collide together is less common than an abstraction or an addition step. But anyway, those are the 3 approaches there for that. Let's see, what else do we need to know in general? Oh, oxygen can function as a radical inhibitor. And oxygen is normally something we try to keep out of a reaction involving radicals. So if you add a radical here with oxygen, you see, you can have the odd electrons come together here. And what do you get? You get the oxygen added on there and a radical here, okay? So this creates a peroxy radical type intermediate. And it's actually part of the damaging effect of fat materials, and we'll see that later on. But here, the oxygen is functioning as a terminator for the carbon radical, and it's making an oxygen radical. In biology, we'll see with vitamin E, there's an important step here of terminating a radical here, where you can abstract a hydrogen atom off of phenol. And what does that give you? It gives you the phenoxy radical, and it gives you HX. So whatever that radical was. to begin with. This gets oxidized in the body further to a quinone, but that can terminate, we say. Vitamin E and vitamin C, we'll see later on, are means of terminating radicals like that. All right, that'll become more clear when we look at some overheads and talk about that. But oxygen can actually terminate radicals. It's detrimental to the reactions we're going to see here in chapter 15. But it also slowly initiates the radical decomposition of fats called autooxidation. That's how fats go rancid. So there's some important radical chemistry here in biology, especially if we talk about inhibition of free radicals in the body, which normally can cause damage, right? So phenols, keep that in mind coming up. Let's look at alkane halogenation, our first reaction that we need to talk about here. So halogenation of alkanes. And this is different. We saw a means of forming halides from alkenes before, right, in chapter 9, but now directly from alkanes. So this is important to talk about. So halogenation of alkanes, very different here. So let's talk about methane plus chlorine and heat or light, okay? Now heat, obviously raising the temperature above room temperature. Light lets you do it at room temperature, which is nice, and we'll see some advantages of light. H nu, that's what, Planck's constant times the frequency of the light. This can be white light. It doesn't have to be ultraviolet light or high energy light. Intense white light is fine to initiate radical chemistry. And what do we get here? We get chloromethane, okay? And our byproduct here is HCl. Yeah, these reactions do become acidic. So that's where that hydrogen came off there. So what type of reaction is this? This is is it elimination? Is it a addition? What is this? No, this is substitution, right? What are we substituting? A hydrogen is being taken off and chlorine's being added. Well, look, we have more hydrogens here. So what else can form here? Well, methylene chloride or dichloromethane also forms, okay? Especially if we're using heat with this process, okay? Even if we try to limit the amount of chlorine in there, we'll often get what? Over halogenation. In fact, that's not the end of the story. We also get what? Chloroform, which is trichloromethane, and we get carbon tetrachloride, okay? So these are often byproducts, even if we try to limit the amount of chlorine. But if we use excess, we can drive it all the way to carbon tet. Okay. Now these all have different boiling points, and I'll show you that in a minute. So it can be practical, whatever there. But if we use light at room temperature instead of heat, and especially if we just use one equivalent here, we can often just get monochlorination, which is very useful. And we'll see that applies for bromination also as well. So let's look at a couple other examples of this. Yeah, let's do bromination. And let's do with light at room temperature. And one equivalence implied there. So what do we get? We get bromocyclohexane, right? And that's great. We go from an alkane, we go to a bromine. And that opens up what? That's a leaving group, right? We can do a lot of other reactions from that. So synthetically, you can see how that's very useful there. And we're doing light and just showing one equivalent. So we just mean mono. If we showed excess here with heat, we'd begin to get di, tri, and eventually all 12 positions could be substituted with bromine, okay? If we add excess in heat and let it go long enough. There's some kinetics here, right? If you limit the amount of time, you'll get more mono. Okay, so there are ways to adjust that. But this shows how versatile it is. How about this one? So propane, and let's do light, one equivalent. Now we got two different positions, right? We have a secondary and a primary position. Cyclohexane, we just had secondary positions, right? But what about here? Well, we're going to get that. That's the secondary one. What other isomers can we possibly get? Well, how about at the primary spot over here? Yeah. How about over here? Well, that would be the same product, right? Okay. So you actually get a mix here. of these stereoisomers. This is a way to keep track of isomers, by the way. How many possible monohalogenation isomers are there here for propane? It's just the two, okay? So we'll get to some more complex examples here that show the utility of this and the complexity of it. But let's look at another alkane here. How about this one? 2-methyl butane, right? And let's chlorinate that with light at room temperature. You don't always have to say the RT. If you just show light with chlorine, you're going to get mono. And let's see, how many possible isomers can we get here? Well, we've got that tertiary one, okay? And do we have a secondary position that's distinct? Yeah, we've got this one. We're going to get a bad mixture, actually, of these. So let's see. And do we have some primary positions that we could get the chlorine on? Yep. How about primary chlorination there? And let's see, these two methyls are the same, right? Because of the symmetry. So we could draw chlorination here. And what? That would be the same as this guy, right? So that's not a distinct isomer. That's the same. Is there another primary position? Oh yeah, what about on this end here? Let's see, chlorine there. Is that distinct from the other ones? Yeah, so we've got this primary one, secondary, and that tertiary one. I think it's only 4, okay? This is not a distinct one, it's the same as that one, okay? So the possibilities here for chlorination is actually going to give us a mixture of things, which is going to be quite problematic there. Let's get into the mechanism now, and we'll revisit the selectivity issue. And the selectivity issue will come out of the discussion on the mechanism. So I think this is a nice thing. Let's look at this reaction. Chlorine with heat, let's just say heat or light, it doesn't matter. One equivalent here. And yeah, if we let it run longer, we'll get over halogenation. But how does this reaction work? Let's look at the elementary steps of the mechanism. Yeah, there are a few steps here. We have what's called the initiation step, which is homolysis of the chlorine-chlorine bond. Okay. We talked about bond dissociation energies way back in chapter 6, I think. Yeah, that's going back there a ways. Can we break that bond homolytically? Yeah, because it is relatively weak. That bond energy is quite low. It's 58 kcals per mole, much lower than a carbon halogen bond or a carbon-carbon bond, which are 90 or so. Let's homolyze that, and in the presence of heat, we can do that. And how does that actually work? Well, we're exciting that bond length, right? So that bond stretch is going on, and we get to the point where we have enough energy where what? It just comes apart. Okay, into what? The 2 chlorine radicals. Okay, and notice there's 7 electron species. They're going to be very reactive, keeping track of your Lewis dot. There's your SOMO thing, the singly occupied thing, and it's 2 of them there. You can also look at this from the point of view of light, right? How does light work here for this? Well, we have the electrons in the sigma bond for that chlorine-chlorine bond, right? We also have what? The sigma star, okay? So what does light do here? Light, a photon of energy, right? It's a little packet of energy. It is a small particle, a photon. It has infinitesimally small mass. It travels with a specific wavelength. And if that wavelength of light corresponds to this gap between the sigma and the sigma star, what can it do? It can promote an electron from the HOMO up into the LUMO orbital, right? And if we do that, what do we have? We have the sigma and the sigma star now populated. What does that do to this bond? It lets it move apart, right? It decouples those 2 electrons in that bond. So electronically, maybe this depiction is a little more rigorous mechanistically applying the principles of quantum mechanics and the molecular orbitals here. But I like this thing with heat, getting that bond length to oscillate enough where it just comes apart. Anyway, that's the initiation step, okay? Now let's look at the propagation steps. Propagation, there'll actually be 2 steps here, okay? And in fact, this initiation step is often just catalytic. We just need a little bit of that to occur. And now the 2 propagation steps are going to take over, actually. So let's see what we need to do here. Propagation, we're going to take chlorine radical and abstract a hydrogen atom from the alkane, okay? So that 1 electron over here, that will combine with this electron in the bond and leave behind an electron. Single hook arrows, right? That means the movement of 1 electron. So what are we going to get? We're going to get ethyl radical plus what? HCl. Oh, good. There's one of our products, right? It is getting acidic here. Yeah, we should have drawn that up here, HCl. Okay. And that's where the H came from for the substitution here, HCl. Well, here we're generating a carbon radical, okay? That's not going to last very long. What else can that do? Well, that can bump into more chlorine, more molecular chlorine, right? And what do we get here? Well, we can abstract a chlorine atom from molecular chlorine. And what do we get here? We get the product. We get ethyl chloride plus what? Chlorine radical. Okay. Notice we just formed the product, okay, which is the key thing we can say. And we formed what? The intermediate for the first propagation step. There it is again. So what? This propagates, we say. This just comes over here and grabs another hydrogen atom off that. We'll need to look at these energies and see why this works. This is actually a pretty stable bond, HCl. We'll see that there. And of course, carbon-hydrogen bonds are very stable, right? This is an unstable bond, this chlorine-chlorine bond. Okay, that's only 58 kcals. But then we make a stable carbon chloride bond, and we regenerate the same intermediate here. We call this a radical chain mechanism. And by chain, we mean what? The propagation steps are linked together, just like links in a chain. They kind of pull each other along. And these will just go back and forth until you consume all the starting material and use up all the molecular chlorine. Notice we don't need to initiate anymore. That's the key thing. This just gets us started, this initiation step with the light or the heat. What propagates and forms the product is the chain, the 2 propagation steps, okay, to form the product and the byproduct there. Now, this can terminate in different ways, and we do have a couple termination steps to talk about. But if this is running fine, those 2 propagation steps will just go until it consumes and forms all the product. We can get a couple terminations to occur here. If 2 chlorine radicals come together, it'll just reform the reagent, which is not degenerate to the reaction. Actually, that can be initiated again. The bad one is this, where 2 carbon radicals can come together and form butane. Now, sometimes trace amounts of these carbon radical coupling products are seen here, but they're very rare. Why is this rare? In fact, these termination steps are both very rare. They're improbable compared to the propagation step. Why is that? Well, it involves 2 radicals coming together. And if those are high energy, less stable intermediates, they're not formed in high amounts. Okay, they're only formed in tiny amounts to get things started and to propagate things. It's much more likely that a radical or high energy thing will react with a closed shell species, an octet thing. 2 open shell species, 2 unstable things coming together is less probable. And that's because the concentrations of these are very low. Okay, there's the concentration. And there I mean very low, which makes their coupling together very improbable. Okay, I think we need to go to the overhead now again and look at a couple of the things there. Here's methane chlorination, which I'm showing here with some of its physical properties here. So In industry, this isn't a bad thing, actually. All of these products are useful. They can sell all of these, okay? Methane, natural gas, whatever, is very cheap. Chlorine, shine a light on or heat it up for a while. If you do it short amount of time, you'll get more of these, methylchlorine. And you can separate those two, right, by their boiling point. So that's not a problem. But if we let it keep going here, we can replace 3 or even all 4 hydrogens to make carbon tet there. That's the highest boiling point. So it doesn't really matter industrially. Do this on ton scale and then just distill these all apart. And you've got multiple products to sell there. So that's often not a problem with the smaller alkanes. Now here's, yeah, the mechanism, which is a little more discussion, and with the numbers here for the bond dissociation energies. And there I said, you know, the bond dissociation or chlorine-chlorine bond, 242 kilojoules, ouch, kilojoules, sorry. Organic chemists, we use kcals per mole. That's 58 kcals per mole. So it's a relatively weak bond. And then that's just initiation, right? That only has to happen a little bit to get things started. So a tiny amount of the chlorine. The rest of the chlorine can be consumed during the propagation step, right? The second propagation step. So the first propagation is with the alkane, abstraction of the hydrogen atom to give the ethyl radical and the byproduct, okay, HCl. And then here's our second propagation, abstracting the chlorine atom from chlorine with the ethyl radical to make our product. Okay, and notice here's chlorine radical being formed. That can go over here and participate in the first propagation step. And these two just keep going, right, until it consumes everything. You don't need to reinitiate things. It can occur if radical coupling occurs with the atomic chlorine radical and form some of that, you can reinitiate it. But generally that termination step is not a problem there. But that's just a little more things there. Oh, and this breaks it out a little more clearly, I think, the 2 propagation steps. And talking about the bond dissociation energies, and look at this, we're breaking this carbon-hydrogen bond. That's 410 kilojoules, so that's a very stable bond. But look, we're forming an even more stable chlorine-hydrogen bond. That's minus 431. So actually that first propagation step is indeed what? Exothermic. And both of these steps for chlorination radical chemistry are actually quite exothermic. And we'll see that has to do with the selectivity as well. And so the second propagation step is then halogenating the ethyl radical, and we get the ethyl chloride product there. And so what, we're breaking the chlorine-chlorine bond, that's the weak one, 58 kcals per mole. And then we're getting a lot of energy out, right, exothermic-wise. So the ones we're forming are negative, right? The ones we're breaking are positive. This goes back to chapter 6, I think, yeah. And so this step here is highly exothermic. And so overall, we're very exothermic. We're over 20 kcals per mole exothermic. So it's generating a lot of heat. And oftentimes you have to cool these reactions down or it'll generate too much heat and boil off your solvent or whatever. So these have to be controlled quite carefully. And plus we're forming HCl, you have to neutralize that with base, whatever. And then often distill out the product, ethyl chloride in this case, but yeah. Okay, let's get into this, the overall energies of the reaction. So if we look at this, our first step with the propagation step, and these are the only ones that are pertinent to the overall energy diagram. That initiation step, we don't need to worry about it because we're just starting out with that initiated here, right? Our first step here is exothermic to form the radical here, and the last one's very exothermic, okay? So overall, we're going to a much more stable compound here. And it's not just we're breaking a carbon-hydrogen bond. You could say that's a more stable bond than a carbon-chlorine bond, but it's the reagents involved in the intermediates, right? And we're forming HCl. So it's the total system that's overall negative in free energy. We can look at individual bonds and say, okay, that's not going to contribute to things. But it's the formation of the HCl and breaking the weak bond in chlorine that really contributes to this overall exothermic process here. But the selectivity is something we need to get into now. Are we forming a primary radical intermediate or a secondary radical? Let's go back to the board and look at selectivity now and talk about some of the factors that might be involved in that. So what are we talking about here? Well, it's where we got this selectivity issue, right, that we looked at before. Let's look at some more examples of that and talk about the factors that might be involved. Now, you might be already thinking, well, that has to do with how stable the radical intermediate's going to be. Primary, less stable than secondary, less stable than tertiary. So substitution of the tertiary position should be, highly favorable. And indeed they are. Let me give you some numbers here. So monochlorination, room temperature, H nu, that stands for the light, the white light. And we're going to get primary here, 28%. Can distill these two apart. And secondary, those are the only two, 72% yield. So, where did these come from? This came from the primary radical, right? Okay, and that's going to be less stable than the secondary radical. So your thinking's correct there. Secondary radical is going to be more stable. And so, yeah, that contributes to more of the product, 72% there. And we can make a prediction here on this one. How about from propane? And that's even simpler, right? So we've got the primary one there, plus the secondary one there. And you might think, well, we'll get a lot more of this, 3 to 1 or whatever. But this one here is only 55%, and this is 45%. One of the things that begins to take over here is what you've got 6 primary hydrogens, right? And you've got 2 secondary hydrogens. Here you had 6 to 4, okay? So you had more positions at the secondary, more stable thing. And then when you have less secondary spots, look, it drops down to about 1 to 1. It's just not very selective. So you can make some predictions there, but let me show you one that's even more complex, actually. And that's with our old friend isooctane. Remember, we looked at this guy, the octane booster. Highly branched here. It's got a lot of different positions to it. Let's look at this one, chlorination. And we're going to do monochlorination. And, how many different sites are there and how many distinct isomeric chlorides are there? So there's a couple ideas going on here. So let's see. Primary position, how about this chloride? And there is that tert-butyl group, and all of these are the same. So that's just one. When this is formed here, it's actually 35% will be this one, okay? Let's see, how about that secondary position, which would be right here? That's a distinct chloride isomer from this one, right? And this one is 26%. Okay, well look, it's even less than the primary one, right? The secondary one, 26%. Now let's see, how about, we've got a tertiary one finally. We've got this one over here, okay? We substitute right there instead, then, but it's only 17%. There's only one tertiary hydrogen, where here on the tert-butyl, there's 9 different hydrogens, right? So it's kind of weighted toward, statistically, how many hydrogens you have at that spot. Is there another isomer here? Yeah, what about this primary spot out on the end here? And I think that's it, because these two are the same there. I think there's 4 possible ones, and this one's 22%. Hopefully that adds up to 100, I don't know. But let's see here. You can't really say that this one is the dominant one at tertiary, or even the secondary one, because they're actually minor compared to this one, which has more hydrogens on it. So we can look at the relative rates here. There's ways to figure this out, and it's just a kinetic effect for chlorine going on here, primary to secondary to tertiary. It turns out to be 1 to 3.8 to 5, okay? So that's actually not much of a preference for chlorination there, okay? 5 times faster at a tertiary spot, so there should be a lot more of this. But look, there's 9 hydrogens here, so that 5 to 1 preference, the rate of formation there, and a tertiary radical is more stable. But here with this tert-butyl group, you have 9 positions, probability-wise, that will form this guy. So that's 35% versus 17%. So that's with the weighted thing. So the bottom line here is chlorine is not too selective. And this practical issue here of forming a monohalide with a complex structure is just not very good. Okay, but let's compare this to bromide and see if we've got an advantage here with bromine and see what we've got. Yeah, we got a couple minutes. Okay, so let's compare chlorination to bromination now and see if we've got an advantage here. So let's pick an example here and compare chlorination and what are we going to get? Tertiary to primary. And look at this, it's 63% primary, 37% tertiary. And there's your statistical thing. There's just a lot more primary positions relative to the one tertiary position. But let's compare this with bromine. Okay, same thing, just having molecular bromine now with this substrate. Look what we get here. We'll get the bromide. And what about the primary bromine? If we measure the percentage, it's 100%. Wow, that's pretty dramatic, okay? And that's an effect where you'd say, well, it's all this tertiary radical. That tertiary radical, right, is going to be much more stable than the primary radical, okay? And where chlorine, jumped on that spot to a great extent and wasn't very selective, bromine will settle for adding to that tertiary position. So what's the main factor here? Yes, it is radical stability, but it also has something to do with the nature of the bromine and the chlorine here. So with bromine, let's do a couple more bromine examples. These are the really useful ones, I think. You'll see when you do synthesis problems, you do a lot of alkane bromination instead. So if you have this substrate here with bromine and light, look at this. You're just going to go right to the more substituted spot, okay? The relative rates here for bromine, for primary to secondary, for tertiary, for bromine radical now is 1 to 82 to 1640. So it's 1,000 times faster to react at the tertiary spots. So you just look for tertiary, and it's much faster than secondary, right? So here, your only product, and that's the only one you need to show for bromination, the most substituted one. And that can be obtained in 93% yield, isolated yield. The other isomers are not there in that purified amount. What about with butane, okay, with bromine and light? Well, you're just going to get the secondary bromine, and that's the only one you need to show. It's highly selective for secondary over primary, okay? And let's do one more. Okay, back to isooctane. Same thing here. So what are we going to do? We're going to go right to that juicy tertiary spot. Okay, that's our only product we need to be concerned with. With chlorine, how many did we have? We had 4 products, right? And they're all kind of equal amounts, really. But with bromine, it's highly selective for the most substitute thing. So let's see this. Let's go to the overheads. We got a minute. Let's try to begin to understand this selectivity issue. So why is bromine so much more selective than chlorine for alkane halogenation? Well, if we look at these steps for forming HBr now in this first propagation step, HBr relative to HCl, HCl is about 85 kcals per mole. HBr is only about 65. It's a lot less stable. So this is actually an endothermic step now for this first propagation step. And when it's endothermic, we're going to a higher level here, right? So if we add up these energies, being endothermic, the transition states here are going to resemble what? Not the starting materials, okay? The transition states are going to resemble in nature the thing they're closest to, which is the higher energy radicals now. Now, by Hammond's postulate, we've invoked that a couple times. the nature of the transition state here resembles what it's closest to in energy on the diagram. So what's it closest to? Well, the intermediates here, because it's endothermic. So this transition state leading to the primary is going to be less stable and higher in energy relative to this transition state leading to the more stable secondary radical. So under these conditions, most of the material will go over this lower barrier. Remember, molecules are lazy. They're not going to want to go over a higher barrier if they have a choice. They're going to wiggle and move around and have just enough energy to get over that point, okay? So this becomes a faster reaction, the one in blue here. Slower reaction is one of that, because bromination is endothermic for that first propagation step. But notice, we already talked about this. For chlorination, this first propagation step is what? Exothermic. So these transition states are going to resemble what? Not these radicals. The transition states are closer in energy to the starting material. And there's really no difference there for those pathways. Okay? So yeah, the one going to the primary one's a little bit higher in energy, but the secondary one you see is closer to it now, leading to the secondary. So there's less differentiation now with this being an exothermic step. Okay? So as this wiggles around, whatever, it has enough energy to really go over both just fine, okay? So no selectivity here if that first propagation step is exothermic. It's Hammond's postulate, but you can kind of see it there, and it has to do with the stability of HBr being less stable than HCl being more stable, okay? You get more energy release here. Here, you got to put energy into it. And that differentiates these two transition states more and leads to higher selectivity. But again, don't sweat that. It's Hammond's postulate. This is allylic halogenation. We'll get to that next time. So yeah, we'll leave it there. We just covered halogenation right now. The bottom line is the best halogen is bromination with Br and light at room temperature. Always go to the more substituted bromine. If you do chlorination, you're going to get a mixture of products, okay? And make sure you can identify all the possible isomeric products that can come out of that. But we'll keep track of that and we'll use it in synthesis problems. Next time we'll do the allylic halogenation, we'll do the anti-Markovnikov, and we'll do the polymerization, those last three. The first one is the most important reaction, the alkane halogenation. Very good. So we'll see you next time on Friday. Thank you.